Okay, good evening, guys. My name is Benjamin. I'm a full stack developer. I'm transitioning from Web2 development to Web3 development, and with the help of this rich hackathon, I'm getting closer to my goal. So basically, my team and I produced a project called GuessNik. It's basically just a two-player game where there are two participants. Basically, there is an asker and there is a guesser. So the asker basically picks a number and the guesser has to guess the number. So the guesser is rewarded based on how close his guess is to the asker's number. Or the asker kind of initiates a wager and the guesser accepts the wager, and the wagers are put in a prize pool, and that is where the rewards are going to be given from. So this is my rich back end for my web app, which was built with React and Reach. So this is the back end. So I'm going to just explain a few things about the code, then we'll move on. So the first line here is just explaining about the Reach versioning system. So this is just Reach version 0.1. So then in line 3 to line 12, what we have here is the function which includes the formula of how we calculate the percentage of the pool that the guesser will be rewarded, that the percentage of the pool that the guesser will be rewarded with based on his guess. So basically, let me explain how it works. Basically, what happens here is that we get the asker's number and the guesser's number. We kind of check the distance, or we subtract the asker's number from the guesser's number, and based on how close it was, would formulate a percentage from this formula. Okay, let's assume that the asker's number is 3 and the guesser's number is 5. So the thing is that because the asker's number is less than the guesser's number, the else block will be run. And so when the else block runs, what it does is that it takes the guesser's number minus the asker's number, which is 5 minus 3, which is 2. So it does 10 subtracts from 2 and you have 8, and 8 multiplied by 10 you have 80. So this means that the guesser gets 80% of the prize pool. So let's create another scenario whereby the asker picks 8 and the guesser picks 2. So because the asker's number is greater than the guesser's number, this if block will run. And what will happen is that the asker's number, which is 8, subtracted from the guesser's number, which is 2, you have 6. 10 minus 6, you have 4. 4 multiplied by 10, you have 40. So the guesser will be rewarded with 40% of the prize pool. So that is how, this is our formula for calculating how much the guesser will be rewarded with based on his guess. So the next couple of code is also a rich application. So this first from line 14 to line 20 is a player object that kind of houses the interact interface for both players. So an interact interface object basically depicts how the front end will interact with the participants of the back end. So basically in this player component, so as I told you, there are two players, the asker and the guesser. So both players can interact with basically these functions. So this has random is an inbuilt function from the rich library. What this does is going to be referred to back in line we're going to look at it back in line 53 and so on, but for now it just basically gets random numbers that will be used for making a salt for encryption of data. So the next thing is the get number function, which is part of the interact interface object. Basically, this is a function that takes no argument but returns an unsigned integer. So this is how the asker or the guesser would be able to give their number to the back end. So the next one is the C outcome. This is a function kind of that takes an integer and returns nothing. This is basically how the back end sends information about the outcome to the front end basically. So the next one is the C number. This is a function that takes two parameters, two arguments. So the two arguments are unsigned integers. This is a function by which the back end sends the numbers of each of the players to the front end so that they can confirm that this is the number that they picked. So then the next part is the inform timeout function. Takes no argument and returns nothing, returns null. So null is nothing. So this is basically a safe function that puts both players on edge. So each of them has a deadline to basically play their number. If you waste time, you get closed out from the game. So the next couple of lines from line 22 till the end, which is line 99, you find the main point, the main entry point of our rich application. So basically this is rich.app, a function that of the function of our the main function of our rich application. So in this place, what we have here is that we have the first part, the first couple of parts, which is from line 23 to line 32, is our application initialization. So in this place, this is where you basically initialize things that your app will need, like initialize the participants of your decentralized application, or initialize the APIs of your decentralized application, or initialize the view of your the views of your interact interface function. Some of these things you can find them on the rich documentation, so you can get more information about that. So this part initializes the two participants of our application. The first participant, which is the asker, and the second participant, which is the guesser. So the participant function basically creates a participant, and it takes a string argument, which is the name of the participant, and an interact interface object. So this interact interface object has three key value pairs. So the first one is the player. So this player kind of is from this object player up here. It basically uses the spread operator to import all the functions and values that are in this object and in this player object, and imports them into this interact interface for the asker. So the next one is the wager, which is an unidentified integer. This is the wager that the asker would send to the back end, or initialize the application with. So basically then the deadline, also the asker has the ability to send the deadline to the back end. So basically what we find here are the functions and values that by which the participants and the front end can interact. Basically this interact interface object is the only way the asker can interact with the front end. So these are only specific to the asker. So now for the guesser, we basically just do the same thing, but we use the spread operator to bring everything from the player object into the interact interface object. Then we now have a function that accepts the wager that the asker initialized the application with. So that is basically it. Then we have next on line 32, we have the init function. Basically this function separates your application initialization part of your main rich application from the steps of your application. So from line 34 downwards, we have the steps of our application. So there are two types of steps. There are the local steps and there are the consensus steps. So basically on line 34, we basically initialize the local step. In this local step, basically we are interacting with the front end, telling them that we are going to inform timeouts for both the guesser and asker. That is what this is function is. This is function basically says that both the asker and guesser can participate in this step of the code of the application. So each asker and guesser, this each says that both the asker and guesser can participate in this step of the application. So the next line we see interact.inform timeout. This is basically how the interaction between the interact interface objects and the front end occurs. So basically you interact dot the function or the value or the key that is in the interact interface object to get the value. So the next step is also a local step that only the asker can be involved in. That's why you have the dot only. So basically in this step we have we ask the asker to send us the wager that he has initialized the application with, and basically we use the interact object to get it. Then we declassify it. Basically in which basically the interaction between the front end and back end is usually encrypted. So we use the classify function to decrypt the encrypted information that have been sent across from the front end to the back end. So in this next line, we declassify the deadline information sent from the front end to our back end only for the asker. Now the next step here is a consensus step. This is a step that is actually stored on the block. This is a step where the information that happens in this step is stored on the blockchain. So the consensus step, we see functions like .publish, .pay, .timeout, .fork, .parallel, reduce, and the rest of them. So here we are publishing the wager information to the blockchain and publishing the deadline information to the blockchain, and then the asker pays the wager. Then the commit function basically just separates the local step from the consensus step basically. So it finalizes and commits the information on the blockchain that and to never be ever be changed again. So that's what the commit step does. If you usually understand what the blockchain does, it's an immutable database that cannot be changed once it has been initialized. So that is kind of what the commit function is doing. Then the next part of our code is from 49 to 51. We are talking about the only this is a local step whereby only the guesser basically interacts with the front end to accept the wager that has been initialized in the blockchain. So basically now when it accepts the wager, when it now the guesser now enters the consensus steps and pays for the wager, and basically this is where this is the timeout function. This is just basically telling the guesser to pay the wager on time, or else he will be timed out. So if the guesser is not comfortable with the wager, this function will be run maybe and takes a while to accept the wager. This function will be run, and basically the guesser is timed out of the game, and basically it closes the application and sends out the wager that the asker has put in the prize pool back to the asker, and informs the players of the timeout. Then we use the commit to separate the consensus step from the local step. So in this next local step, which only the asker can perform, basically gets the asker basically interacts with the front end to get its number, the number that the front end asker choose. Then basically use this make commitment function to basically encrypt the information using a salt. Basically. So this salt is created from these random numbers that are here, from this has random function basically. So this is how it happens. So basically when the information is encrypted, basically it now publishes the commit to the blockchain. Basically when the information is encrypted with a salt, we form a commit. It is this commit that is now stored on the blockchain. So basically in this place the asker publishes the commit, which is the encrypted version of the number, and then basically is required to do it quickly, or else it's going to be timed out, and the game will close, sending all the money back to the guesser, and then informing both players of a timeout. So basically then the next part of our code, as I told, the commit is to separate a local step from a consensus step. Then here this next line on line 69 is basically an assertion that basically asserts or proves that the guesser has no information of the asker's number or the asker's salt. So basically that's why the function is unknowable, meaning that the guesser does not know the asker's number or the asker's salt. The salt, as I told you, is generated from the random numbers and is added on and is prepended or appended to the asker's number to form a commit that has already been published to the blockchain. So this is the next step. The next step is a local step that only the guesser can participate in. Basically the guesser gets its number from the front end and publishes it, basically informing them of a timeout, making them to be aware of a timeout, basically, so that if there's a timeout, so basically you have to publish your number quickly before there's a timeout so that the game can continue. Now we commit this the guesser's number to the blockchain. After that we committed to the blockchain, basically you may be asking, why didn't we encrypt the guesser's number? Basically we didn't encrypt it because because of the asker cannot basically we don't need to actually encrypt it, because we don't need to keep doing heavy work on the blockchain, because actually the blockchain, though it stores data, it doesn't store it in an optimized way, and basically because it doesn't store it in an optimized way, if the source of information on the blockchain basically pay a lot of gas to the blockchain to basically sign your transaction and allow your transaction to be recorded on the blockchain. So that's why we are not encrypting this here, because of the next step we are going to take. So in this next step, basically the asker is asked to publish his salt and his number. So when the asker gets the salt and the number, he publishes them to the blockchain. So now when he publishes his salt and his salt and the number, we basically now check whether the initially published commit is the same with the sort and number. So basically now, if the guesser publishes his number and the asker goes to the blockchain and sees the number and tries to change the number that she initially put to the application, this would revert that quickly, because the salt will change. And basically, if the salt change if the salt changes, basically the commit changes, and everything here is basically is going to return false, and then the entire this thing will be reverted. So that's why this function is here, check commit function. It just basically checks whether the commit that the actor publishes to the blockchain is similar to this number and salt that he publishes currently. So basically, after we have done all these checks, we now basically called our game function that now basically checks looks at the numbers of both the asker and the guesser, and then basically basically checks the how close the guesser's number was from the asker's number, and then rewards the guesser appropriately. So basically, this is a transfer function that transfers funds to the depicted participant. So here we are transfer, because what we are returning here is basically in percentage. So here we are going to basically get the outcome, and you know that our price pool is going to be 2 times of the wager, because the asker initializes the wager and the guesser accepts it. So basically, that's why there is 2 times the wager. So the wager that is the wager is 10 algo, both of them combined is going to be 20 algo. So this is our price pool money. It's going to be 2 times of the wager, which is 20 algo. So using what is done here, basically transfer the outcome of this function to the guesser. Maybe the outcome is 80, so we transfer 80% of price pool to the guesser, and the remaining is transferred to the asker basically. Well, when I submitted this code to my mentor, looked at it and said that it was not kind of optimized, because it was giving some verification errors. Because one good thing that Ridge does is that as it's compiling your code, it really verifies all scenarios and all theorems, making sure that in all scenarios that participants of the applications are honest, and basically the verification process is really nice. So during verification, this throws an error, because basically maybe it's kind of an internal something in Reach, because when dividing a lesser number by a bigger number in Reach, it basically returns 0 when the number is an unidentified integer, because in our application we have been initializing things with unsigned integers. So Reach, that is how Reach works with fixed point. Reach doesn't really there's a way Reach works with fixed point numbers. So in this place now, because if the outcome is 80, we should not expect this thing to return 0.8 based on 80 divided by 100. It will return 0, because it can't return, because this outcome is an unsigned integer. It cannot return a fixed point number. So that is just the problem here. So basically, in this part of my code, I actually got a solution to that kind of with this part of my code. I got a solution to that. So here in this part of the code, we did everything, and basically what we did here is kind of different, making sure that the numerator is going to be bigger than the denominator, and basically we get what the guesser's amount is going to be basically from this formula. So this formula is more optimized, and it doesn't throw any errors. That's basically it. Then basically we commit it, and then inform both the asker and the guesser of the outcome of the game, and inform them of each of their numbers, so they'll know that the game is really fair and just. So from there we can I actually built 2 applications. I built a CLI version. This is the CLI version with an MJS file, and this is the MJS file and all that. Then I also built a web version. So this is the web version I built with React. So you can see the app.js, index.js files and all that, the app.js files and all that. Then I also use Redux so that they can be a single source of truth. Then React works with components and all that. I don't think I can explain that, because the video is getting quite too long. So this index.main.js is the compiled version of our Reach application. So after the compiler runs, this is what it produces, a build folder where you find our index.main.js basically. So this is all about the game GuessNik. um I'm sorry I didn't actually show a video of how this works. I'm having problem with my React. I can't actually spin up a development server currently, so I can't actually show you the front end of the application. And I'm also having problems with Docker and Docker images, so I can't also even spin up the devnet on my system to use it, because I think the Docker image, I don't know about the containers, and I've not used Docker before, so I don't understand what's going on there. But the Docker images and all that are not working properly. But this is basically my code. It is finished. Basically, I've uploaded it to GitHub, so you guys can go to GitHub and see my code. So thank you for all everything. Thanks to Candice, thanks to Estefania, thanks to Jake. This has been a nice hackathon. I've learned a lot about Reach. And when during the meeting, when Candice asked me if I have enough time and unlimited resources, will I keep developing? I said yes, I would, because this is a wonderful programming language. It actually compiles this application and creates a smart contract for you that it's not just how Solidity works, but Solidity allows you to write the smart contract basically. So it gives you kind of an overhead and all that. So because you don't have to put on stress and keep writing smart contracts, you just need to tell Reach about your application in the back end. This is very simple and very similar to JavaScript and all that. So it's a wonderful language, and I would love to develop with it in the future. So thank you. I think I've put enough time with the video. So this is my application, and it is named GuessNik. It's a wonderful game. So when I'm done, so good night, have a nice day, thank you, and God bless you.